Welcome to the Digital Amateur Television Experimenters Night. This is VK7OTC, the club station of the Radio and Electronics Association of Southern Tasmania. Amateur radio is a worldwide hobby that has many different aspects. Digital television is just one of the many modes and areas that are covered. Maybe you're interested in becoming involved in the DATV Experimenters Nights. You realise that you do not have to be a radio amateur or need any ATV equipment to participate anywhere in the world. Also participate in the night by coming up to the Queen's Domain club rooms. Yes, right on top of the Queen's Domain in the heritage-listed Coast Wireless Station. You never know, we might get you in front of the camera or behind doing one of the many roles during the night. We get underway with our program on a Wednesday night from 7:30 p.m. local time. We'll see you soon. This is VK7 OTC.
Saw me.
All right, this is VK7OTC, the club station of the Radio and Electronics Association of Southern Tasmania with our DATV Experimenters Night. And we've got, actually I might go to that camera, Larry VK7WLH. Hello Larry.
Yeah. Hello everyone.
How you going?
Doing okay.
Have a good day?
Not bad.
Now Larry's here with a very special, very nice, very sexy little radio.
Should I hold it up?
You should. Oh, look at that. Now, it's about the size of a cigarette packet. Now, let me just get a cigarette packet here. Not being smokers, it's actually smaller than a cigarette packet.
Yeah.
So there you go. That's the cigarette packet that we found in the ceiling.
Yeah, that's right.
We've got smokers in the ceiling. Now, Larry, tell us about this cute little radio.
Well, this is one of those things when you see it, like I saw it, and I didn't need it, but I wanted it, so I bought it. So there you go. There's part of my pension already.
So there's N+1.
N+1, yes.
N+1.
The radios you need are N+1.
Correct.
Okay,
correct.
so
if we go to here, it's even smaller than a credit card. Because there's a credit card.
Oh, business card, anyhow.
Business card.
Yeah.
So there you go.
Now this is a really crazy radio. First off, you're seeing there, it's looking at 40 meter FT8, right?
Right, okay, cool.
I just had with Richard ZBS, we were outside and we were listening to and heard a Spanish station on sideband from Spain. And on 20 meters and whatever.
With that antenna?
Yeah, just pulled out. Yeah.
Okay.
This is basically a shortwave listening antenna, but receiver, but it's not really intended. Yes. Oh yes. It's small. It's basically a state-of-the-art SDR in a box smaller than a business card. That's what it is, and thicker though. It's Belka-DX, and it's the second version of one. There was a DSP one. It's 1.5 megahertz, right above the broadcast band, to 31 megs.
Oh, there you go.
And it's all mode, which is CW upper sideband it listens. It's got lower sideband, upper sideband, narrow FM, AM1, which is normal envelope detection,
Okay.
and AM2, which is a pseudo. What is that one with the two carriers? They look at the sidebands and compare them. SAM, it's called.
Oh, okay. Okay. Yeah.
Anyhow, it gets rid of a lot of noise. It works
Yeah.
very, very well.
Yeah.
It has adjustable IF, I would call it, although it pretends that it's really audio, but it's not.
Okay.
You can control the lower part of the passband and the upper part of the passband independently.
Okay.
You can set all that. You can control the number of hertz it goes when you turn it. So when you turn the dial, you
Yep.
can,
Yep.
and it automatically defaults to what you might want for each mode you're in. So sideband is one thing,
Okay.
AM is another, FM is another,
And it remembers that for each of the bands, so when you change the bands, it goes back to what you've set it to?
yes,
Yeah.
and it
Okay.
also has 32 memories.
Okay.
So, and it remembers what each of the memories was programmed as. There is a gentleman, DJ0IP,
Okay.
who has a little piece of paper here. We'll throw that in there before we talk about some things.
Whoa. Yeah, okay.
And one of the comments in there, which we'll put up, so it's you may find it easier to read than.
Well,
Notice.
I like the first comment. The radio, it sure is small, very small.
And he tried it in his house. There was a lot of noise.
Okay.
But he has a noisy house, which he
Yep.
says in the bottom line. But it is a communications receiver. It's not your basic little Chinese shortwave listening thingy.
Okay.
And it's fully adjustable. Included, by the way, it has IQ output.
Okay.
And
Yes.
it has an RF gain, an AF gain, and a whole bunch of other stuff. So audio goes in one end, and that's the audio, and then that's the IQ output.
Okay.
And it charges. It has a lithium-ion battery, and it lasts for a whole day of 24 hours of listening on one charge.
And it's only headphones, so it's only an external speaker. It hasn't got a.
Correct.
Yeah,
Now
okay.
they do have the next version, which has a slightly smaller battery, and you take the case off the back, put the other case on, and you've got a speaker. They make one with a speaker,
Oh.
but it has a slightly reduced, playing time.
Because the battery's small.
Yeah.
Yeah.
It's got things like if you push the knob in, it switches things and whatever. But it also,
Oh, yeah.
there you can.
Hang on. Let's go back to.
Yeah, I wanted to mention, by the way, in this piece of paper, he says reception. Now it doesn't have a screen on it. Yeah, the tuning steps are adjustable. That's 10 hertz. That's 50, yeah.
Okay.
It's just turn the knob and it does everything. If you push volume in, hold volume in for a little, just poke volume. Just poke it and leave it go. More. No, hold it. There you are.
Yeah. Okay.
Oh, and it does, by the way, it does the volume, so you can turn the volume up and down. Poke it again.
Oh,
That-
sensitivity.
That's the RF gain.
Okay.
And poke it up and back. Now, if you hit mode, you'll see CW upper, lower,
Look at this.
yes. And the one is that sort of the AM2 is sort of synchronous AM.
Okay.
Okay, so poke mode again. No.
Oh, mode.
Yeah, and now you can set the high cutoff.
Okay.
And since we're in sideband, it thinks
And
it's
the low cutoff.
Yeah.
Yeah.
And when you're in CW, it automatically has a 300 hertz wide CW filter, and you can change the CW offset tone from anywhere from 500 hertz to a kilohertz.
I love it.
Okay. That is the first of 32 memories if you rotate the knob.
Okay. Yes.
And so if you wanted to go to, let's say, 18.1, you just go to 18.1, and no, don't do that. It'll write whatever's on the screen into the memory. But I learned that the hard way. Why is it working?
Oh, yes. It says save.
Yeah, so
versus load.
hit load, yes.
Okay.
And you're right there. And
There
the
you go.
mode is remembered and everything.
I love it.
And the S meter is on the bottom with dBm stuff there or whatever.
Okay,
I don't know.
okay.
I figured that part out. Yeah. And the guy who in Germany who loves radios like crazy, he's DJ0IP. He's a good friend of Robert Sherwood.
Oh, yes. Yes. Sherwood's tests.
Yep. And so he talks about how he connected it inside the house and outside the house. The line which seems interesting is this one. Reception seems on a par with the receiver in my ICOM 7300.
Okay.
Not as easy because it's not a touchscreen, but there you go. And quick rundown, 1.5 to 31 megs. All modes, frequency steps are from 10 hertz up to 50 kilohertz. Adjustable bandwidth, skirts, etc. It's optimized for using this little telescopic antenna, by the way. It really is truly intended to you know,
To
be
use
used
that.
outside. Yeah.
Yeah, okay.
IQ output for hooking up to your software.
Okay, which is that one.
That one exactly. And S meter receivers image rejection is greater than 70 dB. Has a timeout thing in case you're listening in bed and go to sleep, which I've done. You can put it on 20 minutes. You know, you can listen to. Oh, I use it to listen to radio RNZ, Radio New Zealand National.
Okay.
It's on 15. Yeah, that's hard to put on, but.
Oh, that's all right. Nice.
And big difference if you touch that or don't touch it. It really is optimized for that antenna. 5 volt charging.
Yes.
And has a
Little mini USB.
Yeah, and it has a LiPo 2200 milliamp hours.
Okay.
So that's kind of substantial.
Yeah.
Runs around 80 mils current consumption. About the headphone says quarter milliwatt, but yeah. So it's quite a nice toy. And what I'm doing is I'm using it as a return to basics.
Okay.
Because while I've had in my ham career all manner of gear, including most recently a 7300 and 9700, and I currently have a TS 440 SAT, and also a Yaesu FT1000D with all the bells and whistles, only
Okay.
missing the gold knobs. But other than that, but I really want to get back to basics. And so since I like CW and I like FT8 less, but I like to play with it. I'd like to do some parks on the air with this as a receiver, and then use a little CW transmitter, which I have several, and I'm looking at a portable FT8 transmitter, just to get out there on the outside. And because this is, you put it in your pocket.
Well and truly.
It really works well. The filters are astounding because, as I mentioned earlier, you tune to a signal that's there, and you're just tuned off a little bit, and it's just gone.
And it's gone.
They're
Yes,
brick
yes,
wall
yes.
filters. So
Well, there you go. Can I ask a rude question?
yeah,
What's it worth?
200 Australian dollars roughly. Well, it's not. Yeah.
That's nothing.
But I will tell you that I managed to get it as a refugee out of Belarus. They mailed it. It comes
Yeah,
from Belarus,
okay.
like a lot of good stuff does. I got it shipped on the 16th of February.
With bullet holes in there.
Yeah, right. There's no bullet. And I will tell you that it's extraordinarily well made inside, and it reminds me of the stuff that we've been using on 1296. You know, the stuff from Bulgaria.
SG Labs. Well and
Yeah.
truly.
I mean, it's just class stuff. It's beautiful inside.
Oh no, and well, it's beautifully made on the outside. It's a beautiful finish, the whole bit. So, just
That's the whole antenna.
there you go.
I also will tell you it's extraordinary for finding noise in the shack.
Ah, well,
You put it to the band you're interested in and walk around the shack, and you'll know exactly which of those wall warts is causing the problem.
well, that's our actually. If you stick around, that's our next segment is a bit of DFing with. We talked about our Microfox last week. Well, we're now talking about the other end, and I've brought in a little Handi-finder, which I built an awfully long time ago when we were doing lots of fox hunts up here on the domain. But,
All right. Well, this
yes.
doesn't have a directional thing, but it would be
But you could put in a directional antenna.
This is absolutely true. Yeah.
Well and truly.
And the input's calibrated and all that stuff, so you can put it under the microscope there if you want to. It isn't. I didn't need it, but I wanted.
But you've fallen in love with it.
Yeah, well, it's like a long weekend in a bar or something. Anyhow, yeah.
No, that's too much information.
Too much information.
Yeah.
Yeah,
So-
I don't know what it weighs, but it isn't very much.
Oh, no, well, it's not, and it's very, very nice, Larry.
Yeah.
Very, very nice. Belka.DX, and we'll put the website in the description of the video. So
I will give you two. One of them is from the guy who makes it,
okay.
and that's the lowest price, but it comes in a box with bubble wrap around it.
Okay.
That's it.
Okay.
That's all there is.
So
Okay, and the other one comes from some guy who dresses it up a bit and sends it in a nice box, maybe with some earphone or something, and also a manual, but you don't really need a manual, it's online available.
well, and I have to say the user interface is pretty easy to come to grips with.
Yeah, it doesn't have all the touchscreen features and all kinds of other stuff, but it's rather extraordinary, and I haven't yet used it I've only had it a few days.
Yeah.
But I mean, the CW filter and the way it tunes and stuff is just amazing. And as we were outside listening to Spain on 20 meters, just earlier this evening, just with a
Yeah.
just with a
I see
headset.
what you mean with the CW, because it goes into the center frequency, and so you select CW, and then it goes into the center frequency in hertz. So
Yeah, you can adjust
select.
the side tone.
Yeah, yeah.
Oh, it's very sophisticated. I mean, it just knocks the boots off of all those, you know, C. Craig radios and the Texans and everything else.
Oh, yeah. Well, number one for the size. Number two, that's a side tone. And yeah, it's functionality. So there you go.
Well, you can sit on the deck and listen to broadcasts, and I program the FT8 frequencies into it because I want to see what's on.
Yep.
And I use that for listening to FT8 as well as just sort of propagation study.
Yep.
You know, find out what band is open. So, and it would make an extremely good IF if you wanted to put it on. It does all the modes. If you
Well,
want
and you've got the IQ out as
Yep.
to start with. So you wanted to put that into a display or whatever, into some other SDR software.
Yeah.
Hey, that's it. That's fantastic, Larry.
Yeah, good. Yeah.
That is excellent. Excellent. So we'll put the links. If you can send me those links, I'll put them in the description of the video, and people can have a look. But Belka-DX.
Yeah, you could buy it from the other gentleman, the one who sort of dresses it up and has a manual, or you can just save yourself some money and buy it from the maker, which is what I did, and then print the manual out.
Yeah.
So
Okay.
the manual is fundamental.
Okay.
The manual is okay. I mean, this is okay. I mean, somewhere in here, in this multitude of paperwork, there. That's the first and second page of the manual, but the thing you need to look at is on the back page, which I didn't bring.
Let's just zoom out a little bit here.
Yeah, so that's the printed manual online. They warn you not to use a monophonic jack on the earphone because there's some interconnection with something else.
Okay.
So you could short out the audio. And it's got a hefty little amplifier in it, by the way.
Okay.
So they say use stereo only. And so I run it into stereo headset,
Yep.
or I run it into an amplified speaker. I have a little one.
Okay.
So if I want to listen. But they do make a model, and you can buy it as an accessory that has a speaker on the back.
Cool. Fantastic.
All right, all good.
That is fantastic, Larry.
Yeah.
Thank you for sharing that.
It's got a very high fun factor, you know.
So a very high fun factor.
Yeah.
I like that.
Yeah.
You need to do some comments and very high fun factor.
Yeah.
Small. Did I say small? I've
Yeah.
already lost 3 of them. I've had to order more. 'Cause-
And yes, I don't know what the shipping time is now. What with Belarus being what Belarus is, but the guy seems very direct. He's very, very fast on the emails. It's really it's one of
like
those.
the SG Labs guy.
Yeah,
It's phenomenal.
a lot of really good guys out there. SG Labs is wonderful, and QRP Labs. That guy's like a
Correct.
maniac because he's like on top of it. It's just amazing.
Correct. Anyway.
But I think the thing is that individual hams now have taken really sophisticated designs and actually made their own little company, and that really impresses me.
It's fantastic.
Yeah.
It's that grassroots technologist sort of market. That's fantastic.
People committed to them. Yeah. Oh, good. It's a positive thing.
It's a very positive thing. And it's that, that whole support of the open source community and all of that sort of stuff where they make designs and make them freely available. So, in fact, that's an excellent segue.
Yes. Okay.
That's an excellent segue. I'll give you that.
By the way, as a finishing thing, you can lock the screen, you can turn off the screen, and you can lock the frequencies, and you can change the contrast and everything. I didn't show you that part. There's a few other things too. This is
Okay.
Oh.
Now, talking about open source designs. Okay. The open source designs, and I'll just grab. This is definitely an open source design. Now, this doesn't look quite as bad as it seems. There was. I'll just go back here. There was a design that I came across. We were testing direction finding antennas up here for some amateur radio direction findings exercises that we were doing on the domain.
Right.
And we're talking probably 10 to 15 years ago, so quite a while. In fact, when we made the tape measure directional Yagis. And I found this on the web, which is called, and it's actually a registered trademark, it's called the Handi-finder. Handi-finder, so www.handi-finder.com. And it is actually that Handi-finder is a registered trademark. So, but they've made all the information available, and you can buy these readily made, or you can buy the kit. I decided that in true amateur style that I would actually make it based on that design.
Right.
It uses, and you can still get these ICs, it uses a CMOS IC, a 4047, which actually has, it's quite a unique IC, because what it's got in it is a built-in oscillator that you can control with external components, but it also has a flip-flop in it. So a digital flip-flop that enables you to, in this case, we set the oscillator to 1000 Hertz to audio, and we use the flip-flop, which has obviously the output and the complementary output, to switch between one loop or the other. So what it basically does is when you have a signal coming towards the two loops, what it's doing is it's switching from one to the other, and the other loop on here, you'll notice there's a loop, a half-wave loop of coax on the back of here. So one of these is a half wavelength out of phase to the other one.
Right.
So what you end up with is the 1000 Hertz switching is in effect creating a phase difference between one antenna or the other, and you actually hear that at 1000 Hertz. And I'll demonstrate. So what we've got is our Microfox, which we looked at last week. I'll actually turn the Microfox on so you can hear the effect.
I love this.
So we've just turned the Microfox on by plugging in the battery. We stick it back in the film container. So that's going out on 146.550. We'll stick that over there. So we'll switch this on, and you can hear, that's the CW ident on the Microfox, and then it goes into plays a little tune.
I like the tune.
Now, what you can hear.
Right.
Ooh, it actually is overloaded, because that's actually, just unscrew the antenna off of that. We'll do a bit of attenuation with the Microfox, because it's like it's right here. Now, you'll notice on here there are some little arrows I put on here, which is this is the that's better. I should have had that switched in. This is the active loop. So when this loop's pointed towards the source, you'll get the maximum 1000 Hertz tone. So this is how you go. It's over there. Oh, maybe it's that one. Anyway,
That was, yeah.
and one of the problems with this particular that they talk about when they say there is a 180 degree ambiguity with this antenna. You could actually go 180 degrees in the wrong direction, because you actually, if you don't know which of the loops is actually the active loop,
Right, yeah.
you head off in totally the wrong direction.
Oh, so we're pretty close here.
We're incredibly close, which is just if we were to take that sort of out a bit further and create not quite so much and
You want an antenna back?
put the antenna back on again, because it's amazing just having that little stub. Oh, there you go. Because you can null. Which is the arrows. So it's this loop.
Yeah.
Not quite so much signal that way. More signal that way. So anyway, that's the Handi-finder that I made on a little bit of Vera board. Runs off a 9-volt battery. I did check at JK. You can still get these antennas, get these ICs, and I've literally just this is. You make it up for the frequency that you're trying to receive on. So this is made up for 2 meters, and the loop on here obviously is for 2 meters. So it provides that offset, and I've switched that loop in. I can switch that loop in and out. Cardioid at 146. So the cardioid pattern is for this one, and you can also switch that out. You actually switch that out, so it's just one or the other. So anyway, that's the Handi-finder, and I'll put a link to this information in the video description, and you can see there is just literally a little switching arrangement with diodes and resistors and a few little capacitors to each of these loops. The IC, there's some components that set the 1000 hertz oscillator, and then there is an on-off switch, and literally that's it. The rest of it is a bit of engineering to come up with the loops and all of that sort of stuff. So anyway, that's
very nice.
The Handi-finder antenna. I think at the time we said novel design, but probably the Yagis are the bee's knees when it comes to direction finding. But they are sold as noise find, like you were talking about. You go to the frequency you want, and you can find all the noise sources in your house. This was very much, you're trying to find a noise source on 2 meters. This is, you can run around and basically find where the noise is coming from. So by just listening to the tone, so the tone gets stronger when you're pointed. You point the relevant loop at the noise source. So
nice.
There you go.
Yeah.
Anyway, that's a bit of fun.
Fun is important.
Well, a bit of fun that I came across under the house when I was cleaning up over the long weekend, and I thought, I haven't seen this for a long while, and I said, I bet you that battery's flat, and guess what? That battery still has 8.5 volts in it, which is fine to run that CMOS. So there you go. So anyway, that's the Handi-finder.
Two fun little things.
Definitely. You
need to increase your fun factor as you get older.
Yeah, definitely. I agree with that. Definitely agree with that. So thank you, Larry.
My pleasure.
Thank you.
I'll send you the information, and I'll report further when I get a contact.
Fantastic. I look forward to it. I definitely look forward to it. So what we might do, I'll just do a quick update. The Pyranometer, which I showed a little while ago, which is measures sun irradiance. There's a little 180 degrees dual glass dome that focuses the sun onto the sun energy onto a little plate, a little black plate underneath. There is a thermocouple in there that is calibrated, and it gives you a varying resistance based on the amount of energy that's actually hitting this. Kim, VK7KB, with his wonderful contacts in the Antarctic Division, given he works down at the Antarctic Division, went to his contact at Middleton Solar, which is where this is made in out of Melbourne, and they were able to give us the 2 calibration certificates, a copy of the 2 calibration certificates, dated the 25th of January 2010. So for this particular pyranometer, so there is, I'll just show you what's on a calibration. What's on a calibration certificate? Calibration certificate. It's the certificate number, the instrument serial number, which is this particular one, the shortwave sensitivity they have calibrated, so they've made sure that it is 20.45 microvolts per watt per square metre. Response time is about 11.9 seconds, and the internal resistance of the thermocouple is 40 ohms. So there you go, and there's a bit of directional response. And I love, and it's signed off, I love, there's a comment down the bottom, procedure. Shortwave calibration carried out at normal incidence using the reference pyranometer and the sun as a source. ISO 9847 Type 1C. The reference pyranometer is traceable to a world radiometric reference. So annual calibration is recommended. And the other thing that we were able to establish is it came from the hydro, the Hydroelectric Commission. So it was with a whole lot of their test equipment that they were throwing out. So it is an ex-hydro pyranometer, and we managed to get the two 2010 calibration certificates in relation to it. So there you go. Now, I am going to be very brave. I'm going to be very, very brave, and just we'll go to a short break because I need to do a bit of a reset in the studio and get the laptop up here on the table. So, what we're going to be covering is Smith charts. Now, Smith charts, if you've ever done anything in RF engineering, you will know what a Smith chart is. And a Smith chart, I'll put one up here on the screen. A Smith chart is a scary looking thing that looks like this. And it is a fantastic, absolutely fantastic tool for calculating complex impedances, matching networks, SWR, what you can expect from SWR. It is network coefficients. It is all sorts of things that you can use Smith charts for. So what I'm going to do is just take you through the calculation on a Smith chart, the manual calculation on a Smith chart, to come up with a matching network for an actual antenna, so a real antenna. I'll show you the matching network I ended up coming up with, but it's a real example of how to use a Smith chart manually. So this is using these charts, and then I'm going to show you how to do it in a much easier form on using a thing called SimSmith, which is a freeware JavaScript program that enables you to do exactly the same thing, but so much quicker and probably a whole lot more accurately. So what I'm going to do, if we can, what we'll do is we'll just go to the test pattern, and I'll just do a quick reset of the studio and get the laptop up here on the bench next to me. Okay. All right. So now, Smith charts. I have to say, I am well and truly not an expert on Smith charts. I know how to use Smith charts in a very rudimentary way. Most of my information and confirmation came from fantastic videos, and if you haven't seen this guy on YouTube, please go and have a look, because he is one of the ARRL technical editors. He's a guy called Alan Wolke W2AEW, and he is W2AEW. So Whiskey 2 Alpha Echo Whiskey. And he has a whole series of videos, really professionally done videos, on a multitude of RF type subjects, one of which is how to use Smith charts, how to use, there's a whole bucket load on how to use your nano VNA, and in fact we've used some of his material in the past when we've done that. So this particular video, and I'll put a link to it in the video description, so you can go straight to it. But there are a range of other videos that Alan does on Smith charts and how to use Smith charts for a whole range of different functions. So what Smith charts are, he describes a Smith chart as just graph paper, but graph paper that is in circles. And what this circles graph paper actually does is it simplifies a lot of the vector type mathematics that you have to do, the scary mathematics that you have to do. But what the Smith chart enables you to do is do that mathematics but in a graphical form, and so it is just a fantastic tool to come to grips with, and I'll show you the SimSmith equivalent of it, so you can then play with it to your heart's content. So now let's start off. He goes to a right. Okay, now if we zoom in here, you'll notice that I have used the nano VNA to take some measurements of the antenna that I want to use on 30 meters, on 10 megahertz, and the characteristics of that antenna. So the actual antenna physically is about it's about 20 meters long, so there's 20 meters of wire in the air. It's about 6 meters off the ground, and there is also a counterpoise of the same length that runs directly underneath it, and it's in a north-south direction. So at the end of those, and it's end-fed. So at the end that has the two terminations for the counterpoise and the actual antenna, I've put the calibrated nano VNA on there and done a sweep at the particular frequency I wanted at is obviously the digital section of the 30 meter band, and what it's given me is 17.4 of the real ohms and 71.7 of the complex impedance. So the overall impedance is 17.4 plus J 71.7. Now the plus J means that we're talking about the inductive section of the Smith chart, and I'll show you what that actually means. Now the Smith chart as it stands, and this is one of the beauties of a Smith chart, it's actually impedance independent. So what they say is it's a normalized impedance chart, and in this case this is also an admittance chart, and I'll go into what that means in a sec. So right in the center here at 1.0, which is, it can be any impedance you want it to be. Now in most cases the impedance that we're working on is 50 ohms. So everything then needs to be what we say normalized to 50 ohms, so that reference point in the middle of the chart, and this line here on a Smith chart is the pure resistive line. So in the middle is the frequency, the normalized frequency or the standard frequency that you're using. In this case it's going to be 50 ohms. On this side it is the shorted, it's a dead short, and these lines and these circles are progressively, you'll see the scale. If I zoom in here, right in, let's see whether we can see this. Oh, we can. Okay. Let me do... Oh. Now, you'll notice This is the normalized frequency at 1.0. Going in this direction, 0.9, 0.8, all the way through to a dead short at this point here. So that's considered to be a dead short. If we go in the other direction from our normalized frequency, we go, there's the normalized frequency, 1.2, 1.2, 3, 4, 5, all the way over here, and this point here is an open, it's open circuit or infinite resistance. So this line on the, oh, hang on, let wide. This line has definite significance in a Smith chart arrangement. So there is absolutely no reactance at this point in the chart, and of course this is the point. If this is 50 ohms, this is the point with no reactance that we actually want to get to in most cases. So there's absolutely no reactive component to whatever we're actually measuring. Now on a impedance chart, which is these red lines that you can see, that you can readily see, above this line is inductive. So you need to, the reactance is what we call inductive, and below this line is capacitive. So as soon as we go below this line, we're talking a capacitive reactance. Above this line, you're talking an inductive reactance. So that measurement that I took of my hopefully 30 meter antenna, if I plot that on the chart, and what we do here is we've got a resistive component or a real component of, now before I confuse the hell out of everyone, let's zoom in here. We have to, what I was talking about, the chart can be any resistance. And so we've measured this, but to normalize it to 50 ohms, we need to divide each of these by 50. So we divide each of these by 50 and we end up with a normalized impedance of 0.35 ohms of real component and 1.43, J1.43 of the reactive component. So if we plot that on the chart, we've got 0.35 of our real component, so here's 0.3, here's 0.4, so it's right in the middle, and we zoom around this curve, so somewhere up here we've got, it'll cross over with our 1.43, so there's 1.4, there's 1.6. Now our circles are constant resistance, and our arcs that come out here are our reactive components. So these arcs actually are big circles that go off the scale here, but these arcs are the reactive component that come out from the open circuit, and then these are the constant resistance circles. So if we have a real component of 0.35, it's in between there, so it's that circle there, and we come around here and then we find the reactive component of 1.43, which is about there, and it crosses over. So that point right there is where on the Smith chart, there we go, sorry, I was off the show there, I'll go a bit wider. That's where currently our antenna sits with its reactive component on this Smith chart. Now, right up here, and we're supposed to be down here. So you can imagine that the SWR, and in fact you can calculate the SWR. You can draw a circle from our normal point and then cross a line through here until you get to the other side of the circle. Then literally come up to here and then back down to our radially scaled parameters down the bottom, and you can read off the SWR. Now I'm not going to do that tonight, but what we need to do is come up with I'll zoom out a bit more here. What we need to do is come up with a matching network that gets our reactance, our impedance, reactive impedance right here, down to as close as we can to here. Now there's some techniques you've got to use here. One of the techniques, and this is in Alan Wolke's wonderful video, when you have, there's some cheat sheets here that he uses in one of his videos. If your impedance is, and he talks about the yin and yang diagram here, so what he's drawn is, that's 1.0 right in the middle, and you can see he's shaded in this bit. So if your impedance that you measure of your antenna or your load, your ZL here, sits within this area, then what you're looking at is a matching network, which is a series inductor and a parallel or a shunt capacitor here. If it sits down here, it's the reverse, so it's a series capacitor and a shunt inductor, and etc, etc. So there are, ours sits in here, but it actually sits in here as well. So we could have a shunt inductor and a capacitor after the between the inductor and the load, or we could even actually go to a capacitor and a capacitor in different combinations over here as well. So different, there are a number of different networks that will actually enable us to match. What we're going to do is use this one here, which is the parallel, the series inductor and the shunt capacitor. So that's what's drawn up here. So it reminds me. So some of the things that you need to remember with a Smith chart, if you have an inductor that is series, then what you're doing is an inductor in series in this sort of matching network. What you're always doing is you're always moving in a clockwise direction around the Smith chart, and if you've got a capacitor in series, then it's counterclockwise around a Smith chart. Now, if you're then introducing parallel components or shunt components, you need to effectively invert a Smith chart. Now, when you invert a Smith chart, what it becomes is an admittance chart. And it's a bit hard to see. Let me zoom in here a little bit. You can see the impedance chart is the red chart, which is the one that you can see the most. And then sitting underneath that, if you were to flip this over 180 degrees, you can see there's some blue lines, very faint blue lines under here, which is exactly the same chart, but 180 degrees out of phase, or out of 180 degrees turned around. And what they do is they put the impedance chart and the admittance chart on the same thing, because they are effectively the same thing. They're just the invert of each of them. So for a series inductor, it was clockwise on an impedance chart and counterclockwise on an impedance chart for capacitor in series. If you've got a capacitor in shunt or parallel, then it is the inductor in parallel is counterclockwise on the admittance side of the chart, and for the capacitor it's clockwise on the admittance side of the chart. So it's the reverse. So if we keep that in the back of our mind. So what we've done here is we start with here's our load, so we go in this way, we have a look and say, okay, we've got to calculate what we've got to calculate what the capacitor is. So a capacitor in parallel means that we're going clockwise on a admittance chart. So what we're doing is we're trying to get down to the constant circle for our system impedance, which is 50 ohms in this particular case, which is that circle there. So what we do is we come down this line and we're following the blue that's underneath here. You can just see it. And we follow it down, right down until we go through the non-reactance line, the resistant only line. We keep going until we get right down until we hit that 50 ohm line, that normalized 50 ohm line. So we come all the way down here. Now, what we then need to do, that gives us the capacitance value that we can work out from here. So we read off on the admittance chart, it's about 0.65 on the scale here. So it's 0.65 down to 0, which gives us 0.65. And then from 0, we go down here and we read off the admittance chart here where it cuts that line, and it's 0.35. So it's 0.65 plus 0.35, which, surprise, surprise, gives us 1. We then have to invert it because we're talking about the admittance chart. So we invert 1, which is 1. Surprise, surprise. We then normalise that. We times it by 50, and it's times by 50 because we're on the admittance side of the chart. So what we end up with is a capacitive reactance of J50. We use our standard frequency transformed formula, which is 1 over the capacitive reactance times 2 pi r times the frequency. So 50 times 6.283 times 10,137,000, so that's 10 megahertz. And we end up with, here we go, 3.14 times 10 to the minus 10, or 314 picofarads. So that's given us the capacitor. Now, what we need to do is now introduce and calculate the inductor. So what we do is we follow this line, this normalized line, all the way up here to 50 ohms, to 1.0, normalized to 50 ohms, and then we read off. Now, what we're doing here is we're on the impedance side because it's an inductor in series, and what we do is we go clockwise on the inductance side. So we then calculate, we read off the scale and say from here to here, this is 1.0, and sorry, this is 0, and this is 2.5. So we end up with 2.5 as the inductive reactance. So over here, 2.5, we normalise it, and given we're on the impedance side, we don't have to do any inversions or anything. Times 50, which is 125. We've got the formula to give us the inductive reactance. So it's the inductive reactance that we've calculated over 2 pi f, the frequency. We calculate that out and we end up with 1.962 times 10 to the minus 6, which is 1.962 microhenries of inductance. So we've got the 314 picofarads and 1.962 microhenries, which will hopefully get us from here to here. So I know that seems a bit your mind's blowing at about this point. So what I'm now going to show you is how to do this. How to do this in using the wonderful little freeware program called SimSmith. So let's go let's see whether we've got, beautiful. Okay, so what we've got, let me just take a few of these components out. So we'll start with a blank. Okay, let's try that again. Oh, no, sorry. We've got to go right to the bin. That's a bit of a problem with SimSmith, but anyway. Okay, so when you open it up, here's your Smith chart on the screen. This is all JavaScript, which is a fantastic little use of JavaScript. Really, really, really nice use of JavaScript. And what we know is we use Alan's little cheat sheets are with his yin and yang, so we know what sort of network we're looking at. And so what we do is we put that network in, we grab these components down here, and we can put these in. So we've got a capacitor that goes across the load, and we've got an inductor that sits between the capacitor and the generator. So what you'll notice is there's a couple of lines appeared on the Smith chart. What it gives us is this is the line that it put in for the capacitor. So that's the line that we drew on the admittance chart. So it's clockwise on the admittance chart. And you'll notice that it gives us the... now, actually, let's just take... Oh, sorry. Let's just take the inductor out for the time being. Oh, come on. I've got to be quick around here. No, I want to throw it in the bin. That's better. So, okay. So we've introduced the capacitor into this mix. If you right click down here, you'll notice that these are your two. Here's your two normalized constant resistance charts for constant resistance for inductance and constant conductance for your admittance chart. So these are the two circles, and you're looking to get as close as you can to the center of the chart. Now up here we've put in to start with our real and our complex impedance up here as the load. So that's what we've measured on our antenna. So we put in the 17.4 and the 17.7 up here, and what we can do is right click this. See, we're coming down that constant conductance line until we hit that circle for the constant impedance at 50 ohms that we've normalized for. So we're down here. That's fantastic. And it's given us a capacity value of about 320 picofarads, now, which is about close to 314, which we calculated as our doing it manually. Now let's put in the inductor. So we're going to put an inductor in here to complete our little matching network. Now you'll notice there's a little line here that's appeared. If we do a right click here, and you'll notice it's following that normalized line. If we do a right click here and we pull it up, right up to there we go. We pull it right up to the, come on. We pull it right up, that's better. Now, we can pull it right up to our, oh come on, I'm not clicking in the right place, am I? That's better. So we're pulling it up and we're following that normalized line all the way up to what is our normalized 50 ohms, and we're dropping it. So what we've done is capacitor down to here, and then inductor following that line all the way up to hopefully 50 ohms and a good match. Let's read off. What we've done is it's adjusted the capacitance value to 311 picofarads, and the inductor is 1.73 microhenries, which we calculated about 1.9 microhenries. Now, given our margin for error on the chart, on the manual chart, that's probably not bad, and I'd probably believe the SimSmith chart a lot more than I would anything else. However, that gives us now a matching network of 311 or vaguely probably 320 in standard values, and 1.73 microhenries. Now, what does that look like? What does that actually look like when you talk about a real what it looks like in real life? Now, what I've done here is this is a little iron core. I've wound some wire on here, and I've actually empirically measured the inductance. So this is as close as I can get to about 1.8, I think it is, 1.8 microhenries, and then this is a 330 picofarad 630 volt capacitor, which goes across these. This is where the antenna goes onto, and this is where the transmitter goes onto. So this is SO239, and it's just a little matching box. So that is exactly what it looks like to get me to a perfectly matched antenna. Now, you're probably going to ask, is it really a perfectly matched antenna or not? Well, I have to say, I only built this up last night, so I haven't actually put it onto the antenna. That's next week. So I'll actually tell you whether it gets me somewhere near, on 30 metres, it gets me somewhere near a perfectly matched antenna. But I just wanted to point out, that's the manual way of doing it with a Smith chart, and it's fairly tedious, but that's the way they used to do it. And Smith charts, you would have had to have done pages of complex mathematics to work this out, and the Smith chart gives it to you basically in a graphical form. Absolutely magic stuff. Absolutely magic stuff. And the SimSmith program, fully freeware, runs on a range of platforms because it's the Java virtual engine, and it enables you to do a whole bucket load of different types of networks and work out what the values are. Please have a look at Alan Wolke's videos. Whiskey 2 Alpha Echo Whiskey, Alan Wolke, absolutely fantastic, really incredibly knowledgeable guy, and presents in a really easy to understand way. So really worth having a look at his videos. If you have a Nano VNA, honestly, Alan's videos are the place that I would start. I would well and truly start with Alan's videos to find out how you can get the most out of your Nano VNA, and also do really specky stuff like this and be able to tune antennas and understand how an antenna matching unit actually works. There's a wonderful video that Alan has which shows on a Nano VNA what his antenna tuning unit does, as his antenna matching unit actually does, and he talks about the theory and what should be showing on the Smith chart on the Nano VNA. And guess what? He's using the capacitor, variable capacitor, he's using the variable inductor, and he is actually showing you exactly what it's doing to get you somewhere near the center of that chart, and giving you low SWR. So that's all about Smith charts. I have no doubt we'll be doing more with the certainly with the SimSmith program in the not too distant future. Absolutely fantastic little tool. That and a Nano VNA, and you're pretty much set for coming up with tuning antennas and all sorts of stuff. So anyway, okay. Quick reminder. Okay, The April presentation night is Andrew Johns, VK7AJ, giving us a fantastic look at a day in the life of a broadcast audio technician for some of the biggest sporting events that occur in Australia. And he's right there talking to the talent and giving them audio and all sorts of stuff. And there's some really specky stuff. So it should be a great night. And the WIA virtual conference, which is being held down here on the 7th of May. So take a look at the information that's out there. Tonight I've got the presentation by Alan Wolke for our RF viewers for the video and a couple of others which are quite interesting. There's a wonderful, I'm actually doing a reprise of this. Ollie VK7NFI sent in this. There are testing some lithium-ion AA batteries. Now these lithium-ion AA batteries are fantastic from a power density point of view, but the inverters that are in them to drop them down to 1.5 volts are RF crazy noise levels. So you need to be aware that your batteries may be the source of your interference. So yeah, but anyway, that's for our RF viewers. Anyway, that's our program for tonight. Hope you got something out of it. Smith charts, please have a look at the links that I'll put in for the Smith charts and SimSmith. Really helpful little application. This is VK7 OTC, the club station of the Radio and Electronics Association Southern Tasmania, with our DATV Experimenters Night, and we'll catch you next week, 73.